Next question. If x, y, z are uncorrelated and have standard deviation 5, 12, 9 respectively, find the correlation coefficient between u equal to x plus y and v equal to y plus z. We want to find the correlation coefficient between u and v. Okay. And we have also given x, y, z are uncorrelated random variables. X, y, z are uncorrelated. If x and x, y, z are uncorrelated, their covariance between x, y, y, z and x, z are 0. We already studied that. If x, y, z are uncorrelated, we have x, y, z are uncorrelated, then covariance of xy equal to covariance of yz equal to covariance of xz equal to 0. Okay, they are uncorrelated, so their covariance is equal to 0. Now we have another result, the mathematical multiplication theorem on expectation. What is that? If x and y are independent random variables, then expectation of xy equal to expectation of x into expectation of y. Applying here also expectation of xy equal to expectation of x into expectation of y. What's the reason? Because x and y are independent random uncorrelated, so they are independent, so we can use multiplication theorem. Expectation of yz equal to expectation of y into expectation of z, and expectation of xz equal to expectation of x into expectation of z. Clear? Now we have given that x, y, z are uncorrelated and the standard deviation 5, 12, 9 respectively. So what's the variance of x? Variance of x equal to, that is the square of standard deviation, and it is 5 square equal to 25, and variance of y equal to 12 square equal to 144. Variance of z equal to, standard deviation is given 9, so the variance is 81. Clear? Okay. Now we want to find the correlation coefficient between u and v. What's the correlation coefficient between u and v? Correlation coefficient, that is rho uv equal to covariance of uv divided by root of variance of u into root of variance of v. Right. So we want to find covariance of uv. Covariance of uv. So first we want to find expectation of u and expectation of e, expectation of u and expectation of v, and variance of u and variance of v. Okay. Now moving to expectation of u equal to expectation of, what is u? X plus 1. We can write expectation of x plus expectation of y. Okay. What is expectation of v? Equal to expectation of y plus z equal to expectation of y plus expectation of z. Okay. Now what is variance of u? Variance of u equal to variance of x plus 1 equal to variance of x plus variance of y. What is variance of x? Variance of x equal to 25. Variance of y equal to 144. 25 plus 144 equal to 169. Okay. Now variance of v. Variance of v equal to variance of y plus z equal to variance of y plus variance of z. Variance of y equal to 144 and variance of z equal to 81 equal to 225. Now we want to find covariance of uv. Covariance of uv. What's the formula? That is expectation of uv minus expectation of u into expectation of v. Right. That is expectation of uv. What is expectation of uv? Expectation. What is u here? X plus y. What is v here? Y plus z. Minus expectation of x plus y into expectation of y plus z. Okay. Right. Now we can multiply using usual procedure. X in y, xy plus xz plus y square plus yz minus expectation of x plus y equal to expectation of x plus expectation of y into expectation of y plus expectation of z. Okay. Clear? Then expectation of xy plus expectation of x square plus expectation of y square plus expectation of yz minus expectation of x into expectation of y. Expectation of x into expectation of y. Expectation of x into expectation of z minus expectation of x into expectation of z. Okay. Minus expectation of y the whole square minus expectation of y into expectation of z. Okay. Expectation of xy can be written as, by using multiplication theorem, expectation of xy can be written as expectation of x into expectation of y. After simplification, we get expectation of y square minus expectation of y the whole square. This is the formula for variance of y, right? We have given variance of y equal to standard deviation of y equal to 12. So variance of y equal to 144. So covariance of uv equal to 144. Now we want to find rho uv equal to covariance of uv divided by root of variance of u into root of variance of v. Covariance of uv equal to 144. We just calculated 144 divided by root of variance of u. Variance of u we already calculated. Variance of u equal to 169. The root of 169 into root of, it is 225, equal to 144 divided by root of 169 equal to 30 into 50, equal to 0.738. Clear? Next question is, show by an example that independence implies non-correlation but the converse is not true. Okay. The question says that independence implies non-correlation but the converse is not. Converse part is, that is, non-correlation implies independence. That was false. So we want to prove this by using an example. Okay. First we prove the first part, that is independence implies non-correlation. Suppose that let x and y be two independent random variables. Then we know that covariance of xy equal to 0. Okay, we already studied that if x and y are two independent random variables, then covariance of xy equal to 0, which demands rho xy equal to 0. Which demands rho xy equal to 0. If covariance of xy equal to 0, obviously rho xy equal to 0. What's the reason? Rho xy equal to covariance of xy divided by root of variance of x into root of variance of y. If covariance of xy equal to 0, then obviously rho xy equal to 0. Clear? Now we will prove prove the first part. Now we want to prove the converse part. It's not true. Okay. Here we prove the converse by taking an example. Let f of x equal to 1 by 2 minus 1 less than x less than 1, 0 otherwise. Now take let y equal to x square, which says that x and y are not independent. We take x square as y, then we say that x and y are related. So we can say that x and y are not independent. Then e of x equal to, first we want to calculate e of x square, variance, etc. Sorry, covariance, etc. E of x equal to integral minus 1 to 1 x into 1 by 2 dx. 1 by 2 is a constant, can be taken outside. Integral of x equal to x square by 2. Apply upper and lower limit, we get the answer as 0. Next, expectation of y. Expectation of y is nothing but it is x square. X square equal to integral minus 1 to 1 x square into 1 by 2 dx. 1 by 2 can be taken outside. X square, the integral of x square equal to x cube by 3. Applying a lower and upper limit, we get 2 by 6. Okay. Now, expectation of xy equal to expectation of xi. In the place of y, we can write x square, x into x square, x cube. Expectation of x cube equal to integral minus 1 to 1 x cube 1 by 2 dx. 1 by 2 into integral of x cube equal to x raised to 4 by 4. Upper and lower limit apply. We get the answer 0. Okay, now covariance of xy. We know the formula for finding covariance of xy. It is expectation of xy minus expectation of x into expectation of y. Substituting the values, we get 0. That means covariance of xy equal to 0, which demands rho xy equal to 0. We know that if covariance of xy equal to 0, then rho xy must be equal to 0, which means the correlation is equal to 0. We take the variables x and y are not independent, then only we, in this case also we get rho xy equal to 0. Which means that non-correlation need not imply independence always. Clear? So you prove that independence implies non-correlation, but non-correlation need not imply independent always. Okay, that's all about our fourth module. We completed our second semester complementary paper. I hope all of you understand my class. I will give you more questions through WhatsApp. You can ask me doubt through that. Okay. Okay children, take care. Bye bye. See you in the next video.